Hey everyone, and welcome. Today, we are going to tackle acids and bases. Now, I know, you probably think you've got this down from high school chemistry, right? But the story of how we actually define these things, well, it's this amazing story of science constantly upgrading its own rulebook. So, let's dive right in.
So let me start by asking you something. What in the world is the connection between a fluffy cake rising in your oven and the massive, super complex chemistry of our oceans? Well, you guessed it. The answer is an acid-base reaction. But the real story is in how we describe that reaction, because that has changed a lot.
All right, first up, let's head into the kitchen. We're going to uncover the secret chemistry that makes all our favorite baked goods so delicious. And believe it or not, it really all comes down to one magic ingredient.
So, how does this actually work? Well, when you add water to baking powder, it kicks off this little chemical party between an acid salt and good old sodium bicarbonate. And that classic acid-base reaction releases millions and millions of tiny bubbles of carbon dioxide gas. Those are the bubbles that make your dough puff up, giving you that light, airy cake. It's just a perfect little piece of chemistry in action right in your kitchen.
Now, this kind of reaction was first explained using a really simple, almost elegant set of rules. You can think of it as the very first rulebook for acids and bases, written way back in the late 1800s.
The Arrhenius theory is just beautifully straightforward. Basically, an acid is anything that when you dissolve it in water makes more hydrogen ions, H+. And a base, that's anything that makes more hydroxide ions, OH-. See? Simple, clean, and it worked perfectly, as long as you were talking about reactions happening in water.
And here's the textbook example. You mix hydrochloric acid with sodium hydroxide. The H+ and the OH- ions, they get together to form water. And the ions left over, the Na+ and the Cl-, they form a salt. Acid plus base gives you salt and water. It's that neat and tidy neutralization reaction we all had to memorize. But as you know, science rarely stays that neat and tidy for long.
And here's the catch. What happens when there's no water around? What about reactions happening in other liquids, or even between gases? All of a sudden, that first rulebook, the Arrhenius definition, it was just too narrow. It couldn't explain things like ammonia gas acting as a base. Science needed an update, a new chapter.
And this need for an update led to the next huge idea, one that completely reframed the whole concept. Instead of focusing on what's being produced in water, it started focusing on the movement of one single tiny particle, the proton.
So under the Bronsted-Lowry definition, the whole game changes. An acid is just a proton donor. A base is just a proton acceptor. That's it. It's not about making ions in water anymore. It's a dynamic exchange, like a chemical handoff. And this incredibly elegant shift in perspective just blew the doors open on a whole new world of chemistry.
In this new theory, it's not just a small tweak, it is a major, major upgrade. It's not stuck in water anymore. It works in any solvent, even with gases, and it totally changes the way we think about the outcome. Instead of just getting salt and water, the reaction now creates a brand new acid and a brand new base, which we call conjugate pairs. It's just a much more powerful and versatile way of looking at these reactions.
Okay, check out this example. Hydrochloric acid donates its proton to a water molecule. Now wait a minute. Did you see that? Under this new rule, water, which we thought of as neutral, is actually acting as a base because it accepts the proton. The HCl becomes a chloride ion, that's its conjugate base, and the water becomes a hydronium ion, its conjugate acid. It's a complete shift in how we see things.
But what if a reaction doesn't even have a proton to swap? What then? Well, science pushed the boundaries one more time, leading to our final and most powerful definition. This one zooms in even further, to the most fundamental particles of all, the electrons. Okay, so the Lewis theory is the ultimate level up. It completely forgets about protons and just focuses on what's happening at the electronic level. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So it's not a proton swap anymore. It's more like a dance for electrons, all to form a new bond.
So look at this reaction between boron trifluoride and a fluoride ion. There are 0 protons being passed around here, but it's still an acid-base reaction. BF3 has some empty space, so it's ready to accept an electron pair. That makes it the acid. The fluoride ion has a spare pair it's willing to share. That makes it the base. The other two theories just can't explain this.
So let's just quickly trace our journey. We started with Arrhenius, which is great, super simple, but it's stuck in water. From there, Bronsted-Lowry expanded the rules by focusing on that proton so it works anywhere. And then finally, Lewis gives us the biggest, most comprehensive view by focusing on electron pairs, which covers reactions the other two couldn't even touch. You see how each new theory sort of swallows the one before it?
So you might be wondering, why does any of this matter? Why do we need 3 different rule books? Well, it's because chemistry isn't just one simple game. It's a whole universe of different interactions, and you need the right tool for the right job.
And having this complete toolkit is absolutely essential for modern science. We still use the simple Arrhenius rules for basic chemistry in water. We absolutely need Bronsted-Lowry to understand how your own blood maintains its pH, or how our oceans absorb CO2. And the Lewis definition? That is crucial for things like developing new materials or designing huge industrial chemical processes where protons just aren't part of the equation.
So from baking a cake to balancing the chemistry of our planet, our whole understanding is built on these evolving, upgrading definitions. It's such a powerful reminder that in science, the rules are never set in stone. They grow right along with our curiosity. It really makes you wonder, doesn't it? What other simple rules that explain our world are just out there, hiding in plain sight, waiting for their next big upgrade?